Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the crimson silence of Mars as a wandering comet approaches from the depths of space. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the darkness beyond Neptune, something stirs, not with consciousness or intent, but with the slow, inevitable momentum of celestial mechanics. The object designated 3I Atlas, the third confirmed interstellar visitor to our solar system, drifts inward on a trajectory that will carry it past Mars in the coming months. Its nucleus, perhaps 2 kilometers across, contains materials that formed around another star in another stellar nursery, perhaps millions of years ago. Ice and rock compressed in alien cold, now warming in the gentle pull of our sun's gravity. The comet's surface temperature remains locked near absolute zero, but instruments sensitive enough to detect the faintest infrared glow register minute fluctuations. These variations, measured in thousandths of degrees, represent the first whispers of solar energy penetrating layers of primordial ice. The warming occurs at a pace that makes geological time seem hurried. Molecules that have remained motionless for eons begin the subtlest of vibrations, a molecular restlessness that signals the beginning of transformation. Mars turns in its ancient orbit, indifferent to the approaching visitor. The red planet's surface temperature hovers at -80 degrees Celsius in the pre-dawn darkness of its northern hemisphere. Dust storms that once raged for months have settled into stillness, leaving behind rippled dune fields that stretch across plains wider than entire continents. The planet's thin atmosphere, barely a whisper compared to Earth's thick envelope, carries the faintest vibrations across rust-colored landscapes that have remained essentially unchanged for millions of years. Radio telescopes on Earth have begun tracking both objects with patient precision. The signals they detect from Mars arrive as electromagnetic whispers, data packets transmitted by rovers and orbiters that have been humanity's eyes on that distant world for decades. These radio waves, traveling at the speed of light, take between 4 and 24 minutes to reach Earth, depending on the eternal dance of planetary positions. The scientists who receive these signals work in quiet rooms filled with humming computers, translating cosmic static into images of ancient riverbeds and mineral compositions that tell stories older than complex life on Earth. The radio waves themselves become part of the narrative electromagnetic radiation that began as electrical pulses in human-built transmitters, converted to photons that race across the void at precisely 299,792 458 meters per second. They pass through the near vacuum of interplanetary space, carrying digital information about wind speeds, rock compositions, and atmospheric pressures. Some of these signals, scattered by Mars' ionosphere, continue outward toward the stars, bearing inadvertent messages about human curiosity toward distant worlds where no one waits to receive them. But 3I Atlas remains largely silent, too distant and too small to reveal its secrets easily. Astronomers know it follows a hyperbolic orbit, the mathematical signature of an object that will pass through our solar system once and never return. Unlike the elliptical paths of native comets, which loop around the sun in predictable cycles measured in years or centuries, 3II Atlas traces a curve that speaks of infinity. It emerged from the void between stars, will briefly taste the warmth of our solar furnace and will return to that same infinite darkness, carrying with it trace amounts of solar system material. The geometry of its approach reveals profound truths about cosmic motion. Its trajectory, when plotted on astronomical charts, forms a perfect hyperbola, one of the conic sections that ancient Greek mathematicians studied without knowing they were describing the paths of visitors from other stars. The comet's speed relative to the Sun exceeds the escape velocity of our solar system, a mathematical certainty that ensures its departure. No gravitational embrace can capture this wanderer. It moves too quickly through space to be bound by stellar affection. The comet's silence holds mysteries that may never be fully understood. Did it form in the disk around a star now dead? Has it wandered the galaxy for eons? A frozen time capsule carrying the chemical signatures of stellar processes that occurred before our solar system existed. Spectroscopic analysis suggests its composition includes water ice, carbon monoxide, and silicate minerals materials common throughout the galaxy. Yet each grain potentially older than the Sun itself. These questions float unanswered in the cosmic dark, patient as the objects themselves. Mars completes one rotation every 24 hours and 37 minutes, only slightly longer than an Earth day. This fact seems almost impossibly convenient, as if the universe arranged for human sleep cycles to nearly match the rhythm of that distant world. But convenience has nothing to do with planetary mechanics. Mars spins at its current rate because of billions of years of gravitational tugs from the Sun and other planets, a complex dance of forces that has gradually slowed its rotation over geological time. The planet's day lengthens by approximately 2.3 milliseconds per century, an imperceptible drift toward longer nights and extended afternoons. The approaching comet knows nothing of such terrestrial coincidences. It has traveled for millennia in the absolute cold of interstellar space, its surface temperature barely above absolute zero. Now, as it draws closer to the Sun's warmth, that ancient ice begins the first stages of awakening. Molecules that have remained frozen since the formation of distant worlds start to vibrate with increasing energy. The process occurs so gradually that human instruments can barely detect it, but it represents one of the most fundamental transitions in physics, the slow emergence of a comet from its primordial sleep. Between these two objects, the familiar world that humans have studied for centuries, and the alien visitor that may never return to space, continues its ancient business of emptiness. Cosmic dust particles, shed by countless comets over millions of years, drift along gravitational currents, invisible to all but the most sensitive instruments. Solar wind streams outward from the Sun at 400 kilometers per second, carrying charged particles that interact with planetary magnetospheres in displays of physics too subtle for human senses, but perfectly recorded by electronic observers. The approaching encounter between 3I Atlas and Mars represents more than mere celestial coincidence. It marks a moment when materials from two different stellar systems will share the same region of space, their gravitational fields briefly influencing each other in ways too minute to alter either trajectory significantly. The comet will pass Mars at a distance measured in astronomical units, close enough for comparative study, but far enough apart to ensure that neither object disturbs the other's essential nature. This is how the universe conducts its most profound meetings, not with collision or drama, but with the patient crossing of paths in the vastness of space, each object maintaining its essential trajectory while briefly sharing the same corner of the cosmic dark. The comet designated 3I Atlas carries within its frozen nucleus a library written in ice and stone chemical signatures of a stellar system that may no longer exist. Its journey toward the inner solar system began not years or decades ago, but potentially millions of years in the past, when it was ejected from the gravitational embrace of its parent star by the chaotic dance of planetary formation. Since that ancient departure, it has drifted through the galaxy's spiral arms, a cosmic wanderer moving at velocities that make interplanetary travel seem leisurely by comparison. Astronomers estimate that 3I Atlas approaches our solar system at roughly 26 kilometers per second relative to the Sun, a speed that represents the comet's motion through the local standard of rest, the average velocity of stars in our galactic neighborhood. This velocity exceeds the escape velocity of our solar system by a significant margin, confirming beyond doubt that the object originated elsewhere. No gravitational slingshot maneuver around Jupiter or Saturn could accelerate a native solar system object to such speeds. The mathematics of orbital mechanics permit no ambiguity on this point. The comet's hyperbolic trajectory curves through space according to equations first derived by Johannes Kepler 4 centuries ago, when humans had barely begun to imagine that objects could originate beyond the Sun's gravitational domain. Kepler's laws, formulated to describe the elliptical orbits of planets, extend seamlessly to describe the paths of interstellar visitors. The same mathematical principles that govern the motion of Mars also govern the passage of this alien wanderer, demonstrating a cosmic consistency that spans light years and eons. As 3I Atlas draws closer to the Sun, subtle changes begin to manifest in its surface composition. Solar radiation penetrates the outermost layers of primordial ice, causing molecular vibrations that have remained dormant since the comet's formation. Water molecules locked in crystalline structures begin to sublimate directly from solid to gas, bypassing the liquid phase entirely in the near vacuum of space. This process, called outgassing, creates an incredibly tenuous atmosphere around the comet's nucleus, a coma so diffuse that it barely qualifies as matter by earthly standards. The rate of sublimation remains almost negligible at this distance from the Sun, perhaps a few grams per second across the entire surface of the nucleus. This gradual awakening means that 3I Atlas will lose only a tiny fraction of its mass during its passage through the inner solar system. Most of its ancient material will survive the encounter intact, continuing its journey toward distant stars essentially unchanged. The comet serves as an inadvertent time capsule, carrying samples of its birth system toward regions of the galaxy it will not reach for millions of years. Radio astronomers track the comet's approach using interferometric arrays that combine signals from telescopes separated by thousands of kilometers, achieving angular resolution precise enough to detect positional changes measured in milliseconds. These observations reveal minute variations in the comet's trajectory caused by the rocket effect of sublimating gases, a phenomenon so subtle that it requires months of careful measurement to detect. The outgassing creates tiny jets of vapor that act like microscopic rocket engines, altering the comet's path by distances measured in kilometers over the course of its entire passage through the solar system. The chemical composition of these early gas emissions provides clues about conditions in the comet's birth system. Spectroscopic analysis reveals the presence of water vapor, carbon monoxide, and traces of more complex organic molecules, compounds that form in the cold outer regions of protoplanetary disks around young stars. The relative abundances of these molecules suggest that 3I Atlas formed in a stellar environment similar to the outer regions of our own solar system, where temperatures remained low enough for volatile compounds to condense into solid ice. Yet, mysteries persist in the spectroscopic data. Certain isotopic ratios in the comet's outgassing differ subtly from those found in native solar system objects, confirming its extrasolar origin while raising questions about the specific conditions that prevailed during its formation. The deuterium to hydrogen ratio in the water vapor, for instance, suggests formation temperatures slightly different from those inferred for comets in the Kuiper belt. These differences, measured in parts per million, represent chemical fossils of stellar processes that occurred before our Sun condensed from its parent molecular cloud. The comet's surface reflectivity, or albedo, measures approximately 4% darker than charcoal and similar to the carbonaceous material found in the most primitive meteorites. This extreme darkness results from billions of years of exposure to cosmic radiation, which gradually breaks down organic compounds and deposits a layer of carbon-rich residue across the nucleus. The dark surface absorbs solar energy efficiently, driving the sublimation process that creates the comet's tenuous atmosphere. Paradoxically, this darkness also ensures that most of the nucleus remains frozen, as the absorbed energy radiates away into space before it can penetrate deeply into the interior. Ground-based telescopes equipped with adaptive optic systems compensate for atmospheric turbulence to resolve details on the comet's surface as small as a few kilometers across. These observations reveal an irregular, potato-shaped nucleus with regions of varying brightness that suggest compositional differences across the surface. Some areas appear slightly more reflective than others, possibly indicating patches where subsurface ice has been recently exposed by small impacts or thermal stress fractures. The rotation period of 3I Atlas remains uncertain, as astronomers have detected only subtle brightness variations that repeat over intervals of several hours. The comet's rotation axis appears nearly perpendicular to its orbital plane, causing it to tumble through space rather than spinning like a top. This chaotic rotation may result from the gravitational influence of massive planets in its birth system, or from collisions with other small bodies during its journey through interstellar space. The tumbling motion will gradually change as outgassing creates torques that alter the comet's angular momentum. But these changes occur too slowly to observe during its brief passage through our solar system. Navigation specialists calculate that 3I Atlas will reach its closest approach to the Sun in approximately 18 months, passing just inside the orbit of Mars before beginning its long journey back to interstellar space. The gravitational influence of Jupiter and Saturn will slightly deflect its trajectory, adding a few kilometers per second to its departure velocity and ensuring that it leaves our solar system faster than it arrived. This gravitational assist represents an inadvertent gift from our gas giants to the interstellar medium, a tiny contribution of orbital energy that will carry the comet towards stars not yet born when it first began its journey through the cosmic dark. Across the ancient plains of Chryse Planitia, where Viking 1 first touched the Martian surface in 1976, thermal convection cells begin their daily dance as the Sun climbs above the eastern horizon. The temperature differential between the warming surface and the cold atmosphere above creates vertical columns of rising air dust devils that spiral upward with the mathematical precision of fluid dynamics. These whirlwinds, some reaching heights of 20 kilometers, carry microscopic particles of iron oxide and basaltic dust in lazy helical patterns that trace invisible highways through Mars' tenuous sky. The dust devils of Mars move with a deliberate slowness that reflects the planet's reduced atmospheric pressure. Where Earth's tornadoes can achieve wind speeds exceeding 300 kilometers per hour, Martian dust devils rarely exceed 20 kilometers per hour, barely strong enough to lift the finest particles from the regolith. Yet, what they lack in violence, they compensate in persistence. Individual dust devils can maintain their spiral structure for hours, wandering across the landscape like vertical rivers of suspended minerals, visible from orbit as dark tracks that snake across crater floors and ancient lake beds. The particles themselves tell stories written in geological time. Each grain of dust lifted by these thermal columns represents the erosion of rocks that formed billions of years ago, when Mars possessed a thicker atmosphere and flowing water carved the valleys that now lie dry and silent. The iron oxide that gives Mars its distinctive color formed through oxidation processes that required the presence of water vapor, a chemical signature of the planet's more hospitable past, preserved in every mote of airborne dust. Spacecraft orbiting Mars detect these dust devils as brief fluctuations in atmospheric pressure and electromagnetic fields. The charged particles within the spiraling columns create weak electrical currents that produce radio signals detectable by sensitive instruments. These electromagnetic whispers reach Earth as data streams embedded within the routine telemetry from Mars orbiters, arriving as ones and zeros that reconstruct the invisible dance of charged dust in an alien sky. The seasonal rhythm of dust devil formation follows the planet's eccentric orbit around the Sun. During the southern hemisphere's spring and summer, when Mars reaches its closest approach to the Sun, the increased solar heating drives more vigorous convection across the equatorial regions. The number of dust devils detected by orbiting cameras increases dramatically during these periods, sometimes reaching hundreds per day across the hemisphere facing the Sun. Yet, even at peak activity, the total amount of dust lifted into the atmosphere remains modest, perhaps a few tons per day, across the entire planet. Mars's thin atmosphere contains less than 1% of the mass of Earth's atmospheric envelope, creating conditions where the physics of convection operate at the edge of possibility. The atmospheric pressure at the Martian surface averages 6 millibars, equivalent to the pressure found 35 kilometers above Earth's surface, well into the stratosphere. In this rarefied environment, the formation of convection cells requires temperature differentials far greater than those needed on Earth. Yet the resulting air movements remain gentle enough that a human standing in the path of a Martian dust devil would feel only the slightest breeze. The dust lifted by these thermal columns eventually settles back to the surface, but not before traveling vast distances on high-altitude winds that circle the planet at speeds reaching 100 meters per second. Global dust storms, which occur roughly every 3 Martian years, represent the extreme manifestation of this process planet-wide events that can obscure the surface for months and fundamentally alter the atmospheric circulation patterns. During these storms, the normally transparent Martian sky becomes opaque with suspended particles, reducing solar irradiance at the surface by up to 90%. Radio telescopes monitoring Mars during dust storm seasons detect changes in the planet's radio emission patterns as the suspended particles absorb and scatter electromagnetic radiation. The storms create a form of natural radio interference that affects communication with surface rovers and alters the propagation characteristics of signals transmitted between Earth and Mars. Mission planners account for these communication blackouts when designing spacecraft operations, building redundancy into systems that must function reliably despite the planet's capricious atmospheric behavior. The microscopic composition of Martian dust reveals the planet's geological diversity in mineral form. Spectrometric analysis of samples collected by rovers shows a complex mixture of olivine, pyroxene, plagioclase, feldspar, and hematite minerals that formed through volcanic processes during Mars's early history when the planet's interior remained hot enough to drive active volcanism. The relative abundance of these minerals varies across different regions, creating a chemical map of ancient geological processes preserved in the dust that now swirls through the atmosphere. Some dust particles contain trace amounts of sulfur compounds that likely originated from hydrothermal processes, evidence that liquid water once interacted with heated rock beneath the Martian surface. These sulfates represent chemical fossils of conditions that may have supported microbial life, if such life ever arose on Mars. The particles now suspended in dust devils carry these tantalizing clues across continents, mixing materials from diverse geological formations into a homogeneous blend that obscures their original context. The electrical properties of Martian dust devils create phenomena that have no direct analog on Earth. The low atmospheric pressure and extreme dryness of Mars allow static electrical charges to build up on dust particles to levels that would discharge immediately in Earth's humid atmosphere. During large dust storms, this charge separation creates electrical fields strong enough to generate lightning, not the dramatic bolts familiar from terrestrial thunderstorms, but diffuse electrical discharges that occur within the dust clouds themselves. These electrical phenomena produce radio frequency emissions that Mars orbiters detect as sporadic bursts of electromagnetic noise. The signals arrive at Earth as brief interruptions in the otherwise steady stream of scientific data. Electromagnetic signatures of electrical processes occurring in an environment so dry that static charges can persist for hours without dissipating. The phenomenon demonstrates how familiar physical processes, convection, electrification, and electromagnetic radiation operate under conditions so different from those on Earth that they produce entirely novel behaviors. Meteorologists studying Martian atmospheric dynamics have identified patterns in dust devil formation that correlate with the planet's complex topography. The massive volcanic formations of the Tharsis region create thermal anomalies that drive convection cells hundreds of kilometers from the volcanic slopes themselves. Similarly, the deep canyon system of Valles Marineris channels atmospheric flows in ways that enhance dust devil formation along specific corridors, creating preferential pathways for dust transport that have operated for millions of years. The interaction between surface topology and atmospheric circulation creates a form of geological-meteorological coupling that shapes the long-term evolution of the Martian landscape. Dust transported from the polar ice caps gradually accumulates in equatorial regions, while material eroded from the highland, cratered terrain settles in the northern lowlands. This process occurs at rates measured in millimeters per millennium, representing a form of planetary-scale sediment transport that operates on timescales comparable to continental drift on Earth. Radio waves propagate through Mars's tenuous atmosphere with a clarity that would seem impossible on Earth, where water vapor and dense air molecules scatter and absorb electromagnetic radiation across broad frequency bands. The Martian atmosphere, composed primarily of carbon dioxide at a pressure barely 1% that of Earth's sea level, offers minimal resistance to radio transmissions. Signals originating from rovers on the surface reach orbiting spacecraft with remarkable fidelity, carrying digital information across hundreds of kilometers of near vacuum with losses measured in mere decibels. The physics of radio propagation in this rarefied environment creates conditions that radio engineers find both advantageous and challenging. Lower atmospheric density means reduced scattering of electromagnetic waves, allowing precise communication links between surface assets and orbital relays. Yet the same thin atmosphere that enables clear radio transmission also fails to provide the ionospheric reflection properties that enable long-distance radio communication on Earth. Martian radio waves travel in straight lines, limited by the planet's curvature and the line-of-sight constraints that govern all electromagnetic radiation. Mission controllers on Earth receive these Martian radio signals as faint whispers detected by massive dish antennas scattered across multiple continents. The Deep Space Network maintains constant vigil for these transmissions, using 70-meter parabolic reflectors that can detect signals as weak as 10 to the -16th watts power levels, so infinitesimal that the energy received during an entire communication session equals less than the kinetic energy of a falling snowflake. Yet, within these whisper-soft signals lies detailed information about wind speeds, rock compositions, and atmospheric pressures measured on a world 40 million kilometers away. The time delay inherent in interplanetary communication creates a unique rhythm for Mars exploration. Radio signals, traveling at the speed of light, require between 4 and 24 minutes to traverse the distance between Earth and Mars, depending on the relative positions of the planets in their orbits. This delay means that every command sent to a Martian rover must be planned hours in advance, and every response from the rover arrives as a message from the past. Mission operators work within this temporal disconnect, planning sequences of activities that account for the inevitable communication delays. During superior conjunction, when Mars passes behind the Sun from Earth's perspective, solar plasma interferes with radio transmissions for periods lasting up to 2 weeks. The corona's charged particles scatter radio waves in unpredictable patterns, corrupting digital data and rendering communication impossible. Mission planners schedule these periods as communication blackouts, programming spacecraft to operate autonomously while cut off from Earth's guidance. The rovers enter a form of hibernation, performing only essential maintenance tasks while waiting for the planet's orbital motion to restore the communication link. The radio spectrum allocated for deep space communication represents a carefully negotiated resource shared among space agencies worldwide. Mars missions typically operate in the X-band frequency range, using radio waves with frequencies near 8 GHz chosen for their optimal balance between atmospheric penetration and antenna efficiency. At these frequencies, the wavelengths measure approximately 4 centimeters, requiring precise pointing accuracy to maintain communication links across interplanetary distances. Atmospheric conditions on Mars create subtle but measurable effects on radio wave propagation that provide scientists with indirect measurements of meteorological conditions. Changes in atmospheric pressure alter the refractive index of the thin air, causing minute variations in signal arrival times that can be detected by atomic clocks accurate to nanoseconds. These timing variations, called group delay measurements, allow researchers to monitor atmospheric density changes caused by dust storms, seasonal temperature variations, and the daily cycle of atmospheric heating and cooling. The Doppler effect manifests dramatically in Mars-Earth radio communications, as the relative motion between the planets can exceed 20 km per second during certain orbital configurations. This relative velocity shifts radio frequencies by amounts large enough to require constant correction by ground-based receivers. The frequency shifts provide precise measurements of planetary velocities and orbital parameters, contributing to our understanding of solar system dynamics and the subtle gravitational influences that perturb planetary motion over geological time. Interference patterns created by signals reflecting off the Martian surface provide information about surface composition and roughness. Radio waves transmitted from orbiters toward the surface produce echoes that return to the spacecraft after bouncing off rocks, dust, and ice deposits. The strength and polarization characteristics of these reflected signals reveal details about surface materials that complement direct observations from cameras and spectrometers. Smooth surfaces produce strong, coherent reflections, while rough terrain scatters radio energy in multiple directions, weakening the returned signal. The electromagnetic environment around Mars differs fundamentally from that surrounding Earth due to the planet's lack of a global magnetic field. Without magnetospheric protection, Mars's upper atmosphere interacts directly with solar wind particles, creating a complex plasma environment that affects radio wave propagation in ways still being studied. High-energy particles from the Sun create ionization in the upper atmosphere that can cause signal fading and distortion, particularly during periods of enhanced solar activity. Radio astronomy observations conducted from Mars' orbit offer unique perspectives on cosmic radio sources, as the planet's position in the solar system provides a different vantage point for studying distant galaxies and pulsars. The absence of radio frequency interference from human activities makes Mars an ideal platform for sensitive radio observations. though no dedicated radio telescopes have yet been deployed to the planet. Future missions may take advantage of Mars's radio-quiet environment to conduct astronomical observations impossible from Earth's increasingly crowded electromagnetic spectrum. The polarization characteristics of radio waves change as they pass through Mars's atmosphere, providing information about atmospheric composition and the presence of suspended dust particles. Linear polarization becomes partially converted to circular polarization through interactions with asymmetrical molecules and charged particles, creating measurable signatures that reveal atmospheric conditions along the radio path. These polarization measurements complement other remote sensing techniques for monitoring atmospheric dynamics and composition. Digital encoding schemes used for Mars communication employ sophisticated error correction algorithms designed to maintain data integrity despite the challenging propagation environment. Reed-Solomon coding and convolutional encoding add redundancy to transmitted data, allowing ground receivers to reconstruct perfect copies of transmitted information even when portions of the signal are corrupted by noise or interference. The overhead required for this error correction reduces the effective data transmission rate, but ensures reliable delivery of scientific observations across interplanetary distances. The power requirements for Mars communication systems reflect the fundamental challenge of transmitting information across astronomical distances. Rovers typically transmit at power levels of only a few watts, comparable to a small light bulb, yet sophisticated antenna designs and signal processing techniques enable reliable communication with Earth. The inverse square law governing electromagnetic radiation means that doubling the distance between transmitter and receiver reduces signal strength by a factor of 4, creating exponentially increasing power requirements for communication across the solar system. Relay communication through Mars orbiters provides an elegant solution to the power limitations of surface-based transmitters. Rovers can communicate with orbiting spacecraft using relatively low power, while the orbiters use larger antennas and higher transmission power to relay data to Earth. This two-hop communication architecture maximizes the amount of scientific data that can be returned from the Martian surface, while minimizing the mass and power requirements of surface vehicles. The nucleus of 3I Atlas begins its gradual awakening as solar radiation penetrates the outermost layers of primordial ice that have remained undisturbed since the comet's formation around a distant star. At its current distance from the Sun, approximately 4 astronomical units beyond the orbit of Mars, the solar flux reaching the comet's surface measures only 6% of the intensity experienced at Earth's distance. Yet even this attenuated radiation proves sufficient to initiate the molecular processes that will transform the dormant wanderer into an active comet. Water molecules embedded in the crystalline ice structure absorb infrared photons that carry just enough energy to break hydrogen bonds holding the solid matrix together. The transition from solid to vapor occurs directly, bypassing the liquid phase entirely in the near-vacuum conditions surrounding the nucleus. This sublimation process releases individual water molecules at velocities approaching 500 meters per second, fast enough to escape the comet's weak gravitational field and form the beginnings of a tenuous coma around the nucleus. The rate of outgassing remains almost negligible at this early stage, perhaps 10 grams per second across the entire surface of the 2-kilometer nucleus. To put this mass loss in perspective, 3I Atlas loses material at roughly the same rate that a small household humidifier adds water vapor to room air. This gentle awakening ensures that the comet will retain most of its original mass during its passage through the inner solar system, preserving the ancient materials it carries from its birth system for eventual return to interstellar space. Spectroscopic observations detect the first traces of water vapor, carbon monoxide, and carbon dioxide in the expanding coma as these molecules absorb and re-emit solar ultraviolet radiation at characteristic wavelengths. The relative abundances of these species provide clues about the temperature and chemical conditions that prevailed when the comet first condensed from the protoplanetary disk around its parent star. Carbon monoxide, which sublimates at lower temperatures than water ice, appears first in the spectroscopic signatures, followed by water vapor as solar heating penetrates deeper into the nucleus. The coma itself represents one of the most tenuous atmospheres in the solar system, with particle densities so low that individual molecules travel hundreds of kilometers before colliding with another molecule. In this collision-free environment, the gas expands radially outward from the nucleus at constant velocity, forming a spherical envelope that grows larger with each passing day. The boundary between the coma and the surrounding interplanetary medium remains completely invisible to the naked eye, detectable only through sensitive spectroscopic techniques that measure the faint glow of excited molecules. Thermal models of the nucleus suggest that heat conduction into the interior proceeds slowly through the loose aggregate of ice and dust that comprises the comet's structure. The low thermal conductivity of this material, similar to freshly fallen snow, means that solar heating affects only the outermost few centimeters of the surface. Beneath this active layer, the bulk of the nucleus remains at temperatures near absolute zero, preserving chemical compositions that may predate the formation of our solar system. The sublimation process creates microscopic jets of vapor that escape preferentially from areas where the surface composition favors rapid outgassing. These jets, invisible except through their effect on surrounding dust particles, create non-gravitational forces that slightly alter the comet's trajectory. The rocket effect of escaping gases accelerates the nucleus by amounts measured in millimeters per second, but these tiny velocity changes accumulate over months to produce positional shifts detectable by precise astrometric measurements. Dust particles embedded within the sublimating ice become entrained in the expanding gas flow and carried away from the nucleus at velocities determined by their size and the local gas density. The smallest particles, with dimensions measured in micrometers, achieve velocities approaching those of the gas molecules themselves. Larger particles, millimeters in diameter, move more slowly and may fall back to the surface in regions where outgassing rates remain low. This size-dependent sorting process creates compositional variations in the coma that reflect the heterogeneous structure of the nucleus interior. The isotopic composition of the outgassing provides the most direct evidence for the comet's extrasolar origin. The deuterium to hydrogen ratio in water vapor from 3I Atlas differs measurably from that found in solar system comets, suggesting formation conditions distinct from those that prevailed in our protoplanetary nebula. These isotopic signatures represent chemical fossils of nucleosynthetic processes that occurred in the stellar environment where the comet originated, preserved across millions of years of interstellar travel. Radio observations at millimeter wavelengths detect rotational transitions of carbon monoxide and other molecules in the coma, providing measurements of gas temperature and expansion velocity that complement optical spectroscopy. The line profiles of these molecular transitions reveal systematic velocity patterns that indicate non-uniform outgassing across the nucleus surface. Some regions appear more active than others, possibly due to compositional heterogeneities or topographical features that focus solar heating into confined areas. The magnetic field embedded in the solar wind begins to interact with the ionized component of the coma as outgassing rates increase with continued solar heating. Ultraviolet radiation from the sun photoionizes a small fraction of the neutral gas molecules, creating charged particles that respond to electromagnetic forces. The interaction between these newly created ions and the solar wind magnetic field will eventually form the characteristic ion tail that makes comets visible to observers on Earth. Though at this early stage the ionization rate remains too low to produce observable tail formation. Ground-based telescopes equipped with adaptive optics systems strain to resolve structure within the growing coma, but the comet's distance and the inherent faintness of the outgassing make detailed observations challenging. The coma appears as a slightly fuzzy, star-like point in even the largest telescopes, distinguishable from background stars only through its gradual motion against the stellar background and the subtle spectroscopic signatures of molecular emission. Professional astronomers coordinate observation campaigns to track the comet's development as it approaches perihelion, knowing that this may represent their only opportunity to study an active interstellar comet. The dust-to-gas ratio in the early coma provides insights into the formation environment of the comet's parent system. Observations suggest that 3I Atlas contains less dust relative to ice than typical solar system comets, possibly indicating formation in a region where dust grain growth proceeded differently than in our own protoplanetary disk. This compositional difference, if confirmed by continued observations, would represent direct evidence for variations in planet-forming processes around different stars. Computational models of coma dynamics predict that the expanding gas envelope will reach maximum size when the comet achieves its closest approach to the Sun. At that point, the coma may extend several 100,000 kilometers from the nucleus, larger than the distance between Earth and the Moon, yet containing less mass than a small mountain. The contrast between the vast apparent size of an active comet and its tiny actual mass demonstrates the exotic physics of matter distribution in the near-vacuum conditions of interplanetary space. The comet's increasing activity marks the beginning of a transformation that will peak during its passage through the inner solar system before gradually declining as it recedes toward the outer planetary region. This cycle of activation and dormancy, driven entirely by the changing intensity of solar radiation, represents one of the most predictable yet spectacular phenomena in astronomy, the rebirth of an ancient wanderer as it briefly tastes the warmth of an alien star. The Great Canyon system of Valles Marineris stretches across Mars' equatorial region like a geological scar that refuses to heal, extending over 4,000 kilometers from east to west, a distance that would span the entire continental United States. Within this vast network of interconnected chasms lie the fossilized remains of ancient river channels, carved by flowing water during an epoch when Mars possessed a thicker atmosphere and temperatures warm enough to sustain liquid water on its surface. These channels now lie silent beneath layers of rust-colored regolith, their carved geometries preserved in stone as testimony to the planet's more hospitable past. The tributary patterns etched into the canyon walls follow the mathematical principles of dendritic drainage that govern river systems throughout the solar system. Smaller channels converge into larger ones with the same branching angles and length ratios found in terrestrial watersheds, demonstrating that liquid water once obeyed the same physical laws on Mars that govern terrestrial hydrology. The preservation of these patterns in solid rock creates a form of geological photography, capturing the flow dynamics of ancient Martian rivers in permanent mineral form. High-resolution orbital imagery reveals the intimate details of these fossilized waterways with clarity approaching that of aerial photography. Individual boulders transported by ancient floods remain visible on canyon floors, their positions marking the final moments of flowing water that ceased billions of years ago. The spacing and size distribution of these rocks follow patterns consistent with hydraulic sorting, where flowing water naturally segregates sediments according to size and density. Larger boulders cluster in areas where channel constrictions created high-velocity flows, while finer sediments accumulated in broader reaches where water velocities decreased. Spectroscopic analysis of the channel deposits reveals mineralogical signatures consistent with prolonged water-rock interaction under conditions dramatically different from the current Martian environment. Clay minerals identified within the ancient sediments require liquid water for their formation. Yet these same minerals remain stable under current Martian conditions, serving as chemical fossils of a time when the planet's surface chemistry operated in an entirely different regime. The presence of hydrated sulfates and carbonates further confirms that these channels once carried water with dissolved minerals similar to terrestrial groundwater. The depth and width of the largest channels indicate discharge rates comparable to major terrestrial river systems during peak flow conditions. Hydraulic modeling based on channel geometry suggests that some ancient Martian rivers carried water volumes exceeding those of the modern Amazon River, moving billions of liters per second across a landscape that now receives less annual precipitation than the driest deserts on Earth. These massive flows likely persisted for thousands of years, sufficient time to carve the complex channel networks visible in satellite imagery. The termination points of many channel systems occur in topographic basins that show evidence of having contained standing water for extended periods. Sedimentary deposits in these ancient lakebeds display the horizontal layering characteristic of quiet water deposition, contrasting sharply with the chaotic boulder fields found in the channels themselves. Orbital radar has penetrated these sediment layers to reveal buried channel networks that extended beneath the lake surfaces, suggesting that some Martian lakes were fed by groundwater springs in addition to surface runoff. The timing of channel formation coincides with a period in Martian history when the planet's obliquity, the tilt of its rotational axis, differed significantly from its current 25-degree inclination. Computer simulations of Martian climate during periods of higher obliquity show that increased seasonal temperature variations could have driven sufficient atmospheric circulation to transport water vapor from polar ice deposits to equatorial regions, where it precipitated as snow and rain. The correlation between calculated climate conditions and observed geological evidence suggests that orbital mechanics played a crucial role in determining when liquid water could exist on the Martian surface. Crater counting studies of the channel networks provide estimates of their formation ages that cluster around 3.5 billion years ago, during the transition between the Noachian and Hesperian geological periods. This timing corresponds to a fundamental change in Martian atmospheric evolution, when the planet's magnetic field weakened sufficiently to allow solar wind erosion of the atmosphere. The cessation of channel-forming activity coincides with this atmospheric loss, suggesting a direct connection between planetary magnetic field strength and surface water stability. The preservation of these ancient channels requires that erosion rates on modern Mars remain extraordinarily low compared to those on Earth. Calculations based on current dust storm activity and chemical weathering rates suggest that features exposed on the Martian surface erode at rates of only a few nanometers per year, 10,000 times slower than typical terrestrial erosion rates. This remarkable preservation allows geological features billions of years old to remain visible with minimal modification, creating a planetary museum of ancient surface processes. Some channel systems show evidence of multiple episodes of water flow separated by periods of dormancy lasting millions of years. Younger channels sometimes cut through older, partially filled valleys, indicating that conditions suitable for liquid water returned episodically throughout Martian history. The cyclical nature of these flow episodes may reflect long-term variations in the planet's orbital parameters or sporadic volcanic activity that temporarily thickened the atmosphere through outgassing of water vapor and carbon dioxide. The chemistry of minerals found within channel deposits provides constraints on the composition and temperature of ancient Martian water. Iron-bearing minerals show oxidation states that require the presence of dissolved oxygen, while the absence of certain clay minerals that form only in highly acidic conditions suggests that early Martian water was relatively neutral in pH. These chemical indicators paint a picture of ancient Martian surface water that would have been hospitable to life forms similar to terrestrial extremophiles that thrive in cold, alkaline environments. Thermal infrared observations reveal that channel floors retain heat differently than surrounding terrain, creating subtle temperature variations that persist throughout the Martian day-night cycle. These thermal signatures result from differences in rock size distribution and mineral composition between channel deposits and the surrounding bedrock, allowing orbital instruments to map ancient river systems even when they are partially buried by dust. The thermal mapping technique has revealed previously unknown channel networks in regions where optical imagery shows little surface expression. The scale of water flow required to carve the largest channels implies the existence of substantial underground reservoirs that could supply sustained discharge over geological timescales. Subsurface ice deposits discovered by ground-penetrating radar represent possible remnants of these ancient aquifers, now frozen but preserving chemical and isotopic signatures of the water that once flowed across the Martian surface. The spatial distribution of these subsurface ice deposits correlates with the locations of major channel systems, supporting the hypothesis that underground water sources fed many of the ancient rivers. Current models of Martian atmospheric evolution suggest that the transition from a water-rich to a water-poor planet occurred gradually over hundreds of millions of years, with brief periods of increased atmospheric density caused by large impact events or volcanic eruptions. During these temporary atmospheric thickening episodes, conditions may have briefly returned to states that allowed liquid water to flow across the surface, carving new channels or reactivating existing ones. The geological record preserves evidence of these episodic returns to more clement conditions in the form of younger channel systems that cut through older, degraded valleys. The silence that now characterizes these ancient waterways represents one of the most profound transformations in planetary history. The transition of an entire world from conditions that supported flowing water to the frozen desert that Mars has remained for billions of years. Yet the channels themselves persist as monuments to that lost hydrological cycle. Their carved geometry, speaking of processes that once operated under alien skies, now vanished into the deep past. The celestial mechanics governing the motions of both Mars and 3I Atlas operate according to principles so precise that their positions can be calculated decades in advance, with accuracy measured in kilometers across distances spanning astronomical units. This mathematical predictability emerges from Newton's law of universal gravitation, which describes how every particle of matter in the universe attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. The orbital trajectories of both objects trace paths through space that represent solutions to this fundamental equation, executed with the unwavering consistency of cosmic clockwork. Mars follows an elliptical orbit around the Sun with an eccentricity of 0.09355, making its path noticeably more elongated than Earth's nearly circular trajectory. This orbital shape means that Mars experiences significant variations in solar heating throughout its 687-day year. Receiving 45% more solar energy at perihelion than at aphelion, the gravitational influence of Jupiter, with its mass exceeding that of all other planets combined, produces subtle perturbations in Mars's orbit that accumulate over centuries to create measurable changes in orbital parameters. These perturbations follow patterns so regular that astronomers can predict the planet's position thousands of years into the future. The comet 3I Atlas traces a hyperbolic trajectory that represents the mathematical signature of an unbound orbit, a path that curves around the Sun once before extending to infinity. Unlike the closed elliptical orbits of planets, which repeat endlessly in cycles, the comet's hyperbolic path is unique and irreversible. The mathematical parameters that define its trajectory, semi-major axis, eccentricity, inclination, and argument of periapsis encode the comet's entire history of gravitational encounters since it entered the solar system. Each parameter reflects the cumulative influence of every massive body the comet has approached during its inward journey. Orbital mechanics calculations require the integration of gravitational forces from all significant bodies in the solar system, creating a complex mathematical problem known as the n-body problem. While no analytical solution exists for systems containing more than two gravitating bodies, numerical integration techniques allow astronomers to model the motion of Mars and 3I Atlas with extraordinary precision. Modern ephemeris calculations account for the gravitational influences of the Sun, all 8 planets, the largest asteroids, and even relativistic effects predicted by Einstein's general theory of relativity. The timing of the comet's closest approach to Mars results from a fortuitous alignment of orbital geometries that occurs purely by chance. Mars and 3I Atlas will share the same general region of space not because of any causal relationship between their motions, but simply because their independent trajectories happen to intersect in both space and time. The probability of such an encounter between a native planet and an interstellar visitor represents an extraordinary cosmic coincidence, occurring perhaps once every few million years for any given planetary system. Gravitational perturbations from Jupiter and Saturn will slightly modify the comet's trajectory as it passes through the inner solar system, adding approximately 2 kilometers per second to its final departure velocity. This gravitational assist, similar to the techniques used by mission planners to accelerate spacecraft, occurs automatically as a consequence of orbital mechanics. The energy for this acceleration comes from the orbital motion of the giant planets themselves, though the mass difference between the comet and the planets means the effect on planetary orbits remains immeasurably small. The three-dimensional geometry of the comet's approach can be visualized as a hyperbolic arc inclined at 68 degrees to the ecliptic plane, the imaginary surface containing Earth's orbit. This steep inclination means that 3I Atlas approaches the solar system from above the planetary disk, diving through the plane of the planets before climbing back above it during its departure. The unusual trajectory orientation suggests that the comet's motion through the galaxy differs significantly from that of the Sun and planets, confirming its origin in a different stellar system with distinct kinematic properties. Precise measurements of the comet's position rely on astrometric observations that determine celestial coordinates accurate to milliarc seconds, angular measurements equivalent to resolving a golf ball at a distance of 1,000 kilometers. These observations require careful correction for the motion of Earth around the Sun, the rotation of Earth on its axis, atmospheric refraction effects, and the aberration of starlight caused by Earth's orbital velocity. The accumulated precision of hundreds of such measurements allows astronomers to determine the comet's orbital parameters with uncertainties smaller than the gravitational perturbations caused by asteroids. The orbital period of Mars, the time required to complete one revolution around the Sun, measures 686.198 Earth days, a value determined by the planet's average distance from the Sun according to Kepler's third law. This relationship, discovered 4 centuries ago, states that the square of the orbital period equals the cube of the semi-major axis when appropriate units are chosen. The mathematical elegance of this relationship reflects the underlying simplicity of gravitational dynamics, where complex motions emerge from the repeated application of a single fundamental force law. Resonant relationships between planetary orbits create subtle but measurable effects on long-term orbital stability. Mars participates in a complex web of gravitational interactions with other planets that occasionally produce small but cumulative changes in orbital parameters over timescales of millions of years. The most significant of these interactions involves Jupiter, whose gravitational influence can alter Mars's orbital eccentricity by amounts sufficient to affect the planet's climate through changes in seasonal temperature variations. The calculation of precise encounter geometries between Mars and 3I Atlas requires integration of their equations of motion over periods spanning several years, accounting for gravitational forces that change continuously as the objects move through space. Mission designers use similar techniques to plan spacecraft trajectories, though the arrival of an interstellar comet cannot be controlled or optimized through propulsive maneuvers. The encounter represents a natural experiment in celestial mechanics, observable but not manipulable by human intervention. Tidal forces between Mars and the comet remain negligible due to their relatively large separation distance and the comet's small mass. Unlike the dramatic tidal interactions that occur when comets pass very close to massive planets, the Mars 3A Atlas encounter will produce no measurable distortion of either object. The comet's nucleus will retain its original shape and rotation state, while Mars continues its regular motion undisturbed by the presence of its interstellar visitor. The conservation of energy and angular momentum throughout the encounter provides fundamental constraints on the possible outcomes of the gravitational interaction. The total energy of the Mars-Comet system, defined as the sum of kinetic and potential energies, remains constant throughout the encounter, except for minute contributions from solar radiation pressure and outgassing forces. Similarly, the total angular momentum of the system about the Sun cannot change unless external torques act on the objects, ensuring that the overall orbital dynamics follow predictable patterns. Observational verification of predicted encounter parameters will provide a rigorous test of our understanding of solar system dynamics and the accuracy of current planetary ephemerides. Any discrepancies between predicted and observed positions could reveal previously unknown sources of gravitational perturbation or indicate the need for refinements in theoretical models. The encounter thus represents not only a spectacular celestial event, but also an opportunity to validate the mathematical foundations of modern astronomy through direct observation of gravitational dynamics in action. The clockwork precision of orbital mechanics operates on timescales that dwarf human experience. Yet the fundamental equations governing planetary motion were derived by humans working with simple mathematical tools. This achievement represents one of the most successful applications of mathematical analysis to the physical world, demonstrating that the complex choreography of celestial bodies can be understood and predicted through the systematic application of logical reasoning to empirical observations. Spectroscopic analysis of the expanding coma around 3I Atlas reveals a chemical composition that reads like a stellar nursery inventory: water ice, carbon monoxide, carbon dioxide, and traces of more complex organic molecules that formed in the cold outer regions of a protoplanetary disk orbiting a star whose light may no longer illuminate any worlds. The relative abundances of these compounds provide direct evidence for the physical and chemical conditions that prevailed during the comet's formation, offering astronomers a sample of materials that condensed from a stellar environment potentially vastly different from our own solar system's formative epoch. The water molecules detected in the comet's outgassing display isotopic ratios that differ subtly but measurably from those found in terrestrial oceans and solar system comets. The deuterium to hydrogen ratio in 3I Atlas water vapor measures approximately 1.8 times that found in Earth's oceans, a value that suggests formation temperatures slightly lower than those inferred for objects in our outer solar system. This isotopic signature represents a chemical fossil of the thermal conditions that existed in the comet's birth environment, preserved across millions of years of interstellar travel in the form of molecular bonds that encode ancient stellar processes. Carbon monoxide comprises the second most abundant volatile component of the coma, sublimating from the nucleus at temperatures well below those required for water ice vaporization. The CO molecules detected in spectroscopic observations originated from ice that condensed directly from the gas phase at temperatures near 20 Kelvin, conditions so cold that even carbon monoxide, which remains gaseous at terrestrial polar temperatures, freezes into crystalline solids. The preservation of this ultra-volatile component indicates that 3I Atlas has remained cold enough throughout its interstellar journey to retain materials that would have been lost if the comet had approached closer to stellar radiation sources. Trace quantities of methane, ammonia, and hydrogen sulfide appear in high-resolution spectra as faint emission lines that require hours of observation time to detect with confidence. These compounds, present at levels measured in parts per million relative to water vapor, represent the most volatile components of the original icy matrix. Their detection provides evidence that the comet formed in a chemically reducing environment where carbon preferentially combined with hydrogen rather than oxygen, suggesting formation conditions similar to those found in the outer regions of protoplanetary disks, where giant planets accumulate their atmospheric envelopes. The presence of complex organic molecules, including methanol, formaldehyde, and hydrogen cyanide, indicates that basic biochemical precursors form naturally in the comet's parent system through radiation-driven chemistry occurring on grain surfaces in the cold interstellar medium. These molecules, detected through their characteristic rotational and vibrational transitions at radio and infrared wavelengths, represent some of the same compounds that likely provided raw materials for the origin of life on Earth. The discovery of such molecules in an interstellar comet suggests that the chemical foundations for biological processes may be common throughout the galaxy. Dust particles entrained in the expanding gas flow carry additional chemical information about the comet's composition, detectable through the thermal emission and scattered light they produce as they warm in solar radiation. Preliminary analysis of this dust component suggests a composition dominated by silicate minerals, similar to those found in carbonaceous meteorites, the most primitive objects in our solar system. The silicate-to-ice ratio in 3I Atlas appears lower than that found in typical solar system comets, possibly indicating formation in a protoplanetary environment where dust grain growth proceeded differently than in our own solar nebula. Noble gas isotopes trapped within the ice matrix provide additional constraints on the comet's formation environment and subsequent history. Helium-3 to helium-4 ratios reflect the nuclear processes that occurred in the comet's parent star, while neon and argon isotopes preserve signatures of galactic chemical evolution that occurred before the parent system formed. These isotopic measurements require extremely sensitive mass spectrometry techniques, but they offer unique insights into stellar nucleosynthesis processes that operated in environments potentially different from those that produced our Sun. The sulfur-bearing compounds detected in the coma, including sulfur dioxide and hydrogen sulfide, likely originated from sulfur-rich dust grains that accreted along with the ices during comet formation. The oxidation state of these sulfur species provides information about the oxygen fugacity that prevailed during condensation, indicating whether the formation environment was chemically oxidizing or reducing. Current observations suggest conditions intermediate between these extremes, similar to those inferred for the formation region of Jupiter and Saturn in our own solar system. Nitrogen-bearing molecules, particularly hydrogen cyanide and molecular nitrogen itself, represent some of the most challenging species to detect due to their lack of strong spectroscopic transitions at accessible wavelengths. However, these compounds provide crucial information about the nitrogen budget of the comet's formation environment, as nitrogen availability affects the types of organic chemistry that can occur during planetary system formation. The nitrogen-to-carbon ratio in 3I Atlas appears similar to that found in solar system objects, suggesting similar stellar nucleosynthesis histories despite the comet's extrasolar origin. The temporal evolution of outgassing rates as the comet approaches the Sun reveals information about the physical structure of the nucleus and the distribution of volatile compounds within its interior. Early observations show that carbon monoxide begins outgassing at much greater distances from the Sun than water vapor, indicating a layered structure where the most volatile compounds concentrate near the surface. This compositional stratification may result from thermal processing during the comet's journey through interstellar space, where cosmic ray heating gradually altered the distribution of volatile species within the nucleus. Photodissociation processes driven by solar ultraviolet radiation create daughter products in the coma that provide indirect information about parent molecules sublimating from the nucleus. Hydroxyl radicals produced by water vapor photodissociation and carbon atoms created by carbon monoxide dissociation can be detected at wavelengths where the parent molecules themselves produce weak or unobservable signals. The spatial distribution of these daughter products within the coma reveals information about gas expansion velocities and the efficiency of photochemical processes in the near-vacuum conditions surrounding the nucleus. The magnetic field measurements obtained from spacecraft in the solar wind can detect the interaction between the comet's ionized coma and the interplanetary magnetic field, providing additional constraints on the composition and production rate of ionizable species. As solar ultraviolet radiation photoionizes molecules in the expanding coma, the resulting charged particles become coupled to magnetic field lines embedded in the solar wind. The strength and orientation of magnetic field perturbations caused by this interaction provide remote measurements of ionization rates that complement direct spectroscopic observations. Comparison of the chemical composition of 3I Atlas with that of solar system comets reveals both similarities and subtle differences that illuminate the diversity of chemical processes operating during planetary system formation throughout the galaxy. While the major volatile components, water, carbon monoxide, and carbon dioxide, appear common to comets regardless of their origin, minor species and isotopic ratios show variations that reflect the specific conditions prevailing in different stellar environments. These chemical fingerprints provide astronomers with tools for identifying the stellar origins of future interstellar visitors. The gradual increase in outgassing rates as 3I Atlas approaches perihelion will provide opportunities for more detailed chemical analysis as signal-to-noise ratios improve with increasing molecular production rates. Advanced spectroscopic techniques, including high-resolution interferometry and space-based observations above Earth's atmospheric absorption lines, may reveal additional trace species that remain below detection thresholds at the comet's current distance from the Sun. Each newly detected molecule adds another piece to the chemical puzzle of stellar system formation occurring around distant stars. The chemical inventory carried by 3I Atlas represents a form of interstellar archaeology, preserving molecular fossils of conditions that existed in another stellar system millions of years ago. These chemical signatures, locked within crystalline ice structures and slowly released as the comet approaches our Sun, provide direct samples of materials that formed under alien skies and now offer their secrets to human instruments designed to decipher the universal language of molecular spectroscopy. The polar ice caps of Mars undergo their ancient rhythm of advance and retreat with the mathematical precision of a planetary metronome, each cycle driven by the seasonal variations in solar heating that have repeated for millions of years with scarcely any variation. The southern polar cap, composed primarily of frozen carbon dioxide with underlying layers of water ice, expands during the Martian winter to cover an area larger than the continental United States before retreating to a residual cap barely 100 kilometers across during the height of summer. This dramatic transformation occurs as atmospheric carbon dioxide freezes directly from the gaseous state onto the polar surface when temperatures drop below -125 degrees Celsius. The physics governing this seasonal cycle operates according to the same thermodynamic principles that control phase transitions throughout the universe. Yet the specific conditions on Mars create behaviors unlike those found anywhere else in the solar system. The low atmospheric pressure, averaging 6 millibars at the surface, places the carbon dioxide cycle near the triple point where solid, liquid, and gaseous phases can coexist. Under these conditions, frozen carbon dioxide sublimates directly to vapor without passing through a liquid phase, creating atmospheric pressure variations that drive global wind patterns and weather systems. Orbital observations reveal the intricate structure of the advancing ice cap as it spreads across the polar landscape each autumn. The carbon dioxide frost does not deposit uniformly, but follows topographical features and thermal gradients that create complex patterns visible from space. Dark spots and channels appear within the expanding ice sheet, where subsurface heating or wind effects prevent frost accumulation, creating a mottled appearance that changes daily as atmospheric conditions fluctuate. These patterns serve as visible markers of the atmospheric dynamics operating in Mars' thin envelope of air. The total mass of carbon dioxide that cycles between the atmosphere and polar caps represents approximately 25% of Mars' entire atmospheric inventory. During southern winter, enough atmospheric gas freezes onto the polar surface to reduce global atmospheric pressure by several percent, a pressure change large enough to affect the operation of scientific instruments and the flight characteristics of aerial vehicles operating in the Martian atmosphere. This massive seasonal redistribution of atmospheric mass has no analog in Earth's climate system, where water vapor cycles represent only a tiny fraction of atmospheric composition. Subsurface radar observations penetrate the polar ice deposits to reveal layered structures that preserve records of Martian climate variations extending back millions of years. These polar layered deposits consist of alternating bands of water ice and dust that accumulated during periods when Mars's orbital parameters differed from their current values. Changes in the planet's axial tilt, orbital eccentricity, and precession cycle combine to create complex climate patterns that operate on timescales from thousands to millions of years, each leaving distinctive signatures in the polar stratigraphy. The retreat of the seasonal carbon dioxide cap during spring and summer occurs with dramatic speed once temperatures rise above the sublimation point. Thermal infrared observations show that the ice edge can retreat several kilometers per day during peak sublimation periods, creating atmospheric disturbances that propagate across the planet as pressure waves. The rapid phase change from solid to gas releases latent heat that further accelerates the sublimation process, creating positive feedback loops that ensure complete removal of seasonal frost within a few months. Wind patterns generated by the sublimating polar cap create some of the most powerful atmospheric circulation features observed on Mars. Katabatic winds, flowing downslope from the polar plateau at velocities exceeding 100 meters per second, carry dust and water vapor across vast distances before depositing these materials in equatorial regions. These seasonal wind systems transport enough material to gradually alter surface topography over geological timescales, creating subtle but measurable changes in crater rim profiles and dune field configurations. The chemical composition of the polar ice varies with depth and location, reflecting the complex interplay between atmospheric dynamics and surface chemistry that has operated throughout Martian history. Water ice predominates in the deeper layers of both polar caps, while seasonal carbon dioxide frost forms only thin surface veneers during winter months. Dust layers embedded within the ice preserve atmospheric compositions from past epochs, including trace gases that provide clues about ancient volcanic activity and possible biological processes. Spectroscopic analysis of polar ice reveals isotopic signatures that constrain models of atmospheric evolution over geological time. The deuterium to hydrogen ratio in polar water ice differs slightly from that found in the current atmospheric water vapor, suggesting that significant atmospheric loss has occurred since the ice deposits formed. These isotopic variations provide quantitative measures of the rates at which Mars has lost its atmosphere to space, driven by solar wind erosion and thermal escape processes operating over billions of years. The thermal properties of Martian polar ice create temperature gradients that drive sublimation at rates determined by local energy balance considerations. Surface ice temperatures track atmospheric temperatures closely, but subsurface temperatures respond more slowly to seasonal variations due to the low thermal conductivity of the ice-dust mixture. This thermal lag creates conditions where subsurface ice can begin sublimating before surface temperatures rise above the phase transition point, leading to the formation of subsurface cavities and eventual surface collapse features. Seasonal variations in polar ice coverage affect global atmospheric dynamics by altering the planet's energy balance and atmospheric circulation patterns. The high albedo of fresh carbon dioxide frost reflects solar energy efficiently, creating cold spots that enhance atmospheric circulation between polar and equatorial regions. As the seasonal ice retreats, darker underlying surfaces absorb more solar energy, creating thermal contrasts that drive dust storms and other weather phenomena observable from Earth-based telescopes. The interaction between polar ice and atmospheric dust creates feedback mechanisms that influence the rate and extent of seasonal cap formation. Dust particles embedded within freshly deposited frost reduce the ice's reflectivity, causing enhanced absorption of solar radiation that accelerates sublimation rates. Conversely, dust-free ice deposits remain stable longer due to their higher albedo, creating spatial variations in ice persistence that correlate with regional dust storm activity patterns. Carbon dioxide geysers observed during polar spring represent one of the most spectacular manifestations of the seasonal ice cycle. These features occur when solar heating warms dark material beneath translucent ice layers, creating pressurized gas pockets that eventually break through the surface in explosive releases. The resulting jets of gas and dust can reach heights of several kilometers, creating dark, fan-shaped deposits on the ice surface that remain visible for months after the geyser activity ceases. Long-term monitoring of polar ice variations reveals subtle changes that may reflect ongoing climate evolution driven by orbital parameter variations. The residual southern polar cap appears to be shrinking gradually over decadal timescales, possibly indicating a long-term warming trend related to the planet's current orbital configuration. These changes occur slowly enough that they require decades of consistent observation to distinguish from normal, seasonal, and interannual variability. The polar ice caps serve as reservoirs for atmospheric gases that become available for redistribution during sublimation events. Noble gases trapped within the ice matrix preserve samples of ancient Martian atmosphere, while trace organic compounds may record evidence of past biological activity if such processes ever occurred on Mars. The seasonal release and recapture of these materials creates opportunities for chemical reactions that might not occur under the stable conditions found in temperate regions. Future climate evolution on Mars will continue to be dominated by the orbital forcing that drives polar ice cycles, but human activities may eventually introduce perturbations to this ancient rhythm. Proposed terraforming scenarios involve deliberately altering polar ice dynamics to increase atmospheric pressure and temperature, potentially ending the carbon dioxide freeze-thaw cycle that has operated unchanged for millions of years. Until such interventions occur, the polar caps will continue their eternal dance of advance and retreat, marking the passage of Martian seasons with the reliability of a cosmic calendar. Microscopic particles shed by 3I Atlas join an invisible river of cosmic debris that flows continuously through interplanetary space, adding interstellar material to the steady stream of dust produced by asteroids, comets, and planetary ring systems within our solar system. These particles, ranging in size from nanometers to millimeters, travel at velocities determined by the gravitational and radiation forces acting upon them as they drift away from their parent bodies. The smallest grains, pushed by solar radiation pressure, can achieve velocities exceeding the escape velocity of the solar system, while larger particles follow more complex trajectories influenced primarily by gravitational forces. The production rate of dust from the comet's nucleus remains modest at its current distance from the Sun, perhaps a few grams per second distributed across particles spanning 6 orders of magnitude in size. Individual dust grains consist of silicate minerals, organic compounds, and trace metals that condensed from the protoplanetary disk surrounding the comet's parent star millions of years ago. These microscopic fragments carry chemical information about stellar nucleosynthesis processes that occurred in an entirely different galactic environment, now dispersed through our solar system's gravitational domain as inadvertent samples of extrasolar planet formation. The dynamics governing dust particle motion in the solar wind environment create complex trajectories that depend sensitively on particle size, composition, and the local electromagnetic conditions. Particles smaller than 1 micrometer become coupled to the solar wind magnetic field through electromagnetic forces, causing them to spiral along field lines as they propagate outward from the Sun. Larger particles, less affected by electromagnetic forces, follow ballistic trajectories modified primarily by solar radiation pressure and the gravitational attraction of nearby planets. Instruments aboard spacecraft operating throughout the solar system detect these dust particles as brief electromagnetic pulses generated when high-velocity grains impact detector surfaces. The Ulysses spacecraft, orbiting the Sun in a polar trajectory, has recorded impacts from interstellar dust particles for over a decade, providing direct measurements of the composition and flux of material entering our solar system from galactic sources. The addition of dust from 3I Atlas to this background flux will remain undetectable except through statistical analysis of impact rates correlated with the comet's orbital position. The size distribution of particles ejected from the comet follows a power law relationship where smaller particles vastly outnumber larger ones, a pattern consistent with fractal fragmentation processes operating during the sublimation of ice dust aggregates. For every grain visible to the naked eye, roughly 1 millimeter in diameter, millions of submicron particles escape the nucleus and join the interplanetary medium. This size distribution ensures that the vast majority of mass lost by the comet takes the form of particles too small to observe individually, detectable only through their collective effects on scattered sunlight and thermal emission. Solar radiation pressure acts as a selective force that preferentially removes smaller particles from the inner solar system while allowing larger grains to remain in stable orbits around the Sun. Particles smaller than 1 micrometer experience radiation pressure forces that exceed solar gravitational attraction, causing them to spiral outward and eventually escape the solar system entirely. This size-dependent sorting mechanism means that dust populations observed in the inner solar system represent primarily the larger particles that can resist radiation pressure, while the more numerous smaller grains migrate continuously outward toward interstellar space. The interaction between solar wind plasma and dust particles creates charging effects that alter particle trajectories through electromagnetic forces. Dust grains acquire electrical charges through photoemission and plasma bombardment, reaching electrostatic potentials of several volts relative to the surrounding plasma. These charged particles then respond to electric and magnetic fields embedded in the solar wind, creating complex motions that can trap particles in resonant orbits or accelerate them to velocities exceeding their initial ejection speeds from parent bodies. Zodiacal light, the faint glow visible in Earth's sky before dawn and after sunset, results from sunlight scattered by the population of dust particles orbiting within the inner solar system. The contribution from 3I Atlas to this phenomenon will remain negligible due to the small amount of material ejected during the comet's passage. But the interstellar origin of these particles means that photons scattered by this dust carry information about extrasolar materials directly to observers on Earth. The polarization and color properties of scattered light provide remote sensing capabilities for studying dust composition and size distributions. Ground-based radar systems occasionally detect meteor showers associated with comet encounters, but the low particle production rate and unfavorable geometry of the 3I Atlas approach make such observations unlikely. The comet's trajectory carries it through regions of space where ejected particles will not intersect Earth's orbit, ensuring that terrestrial observers will not experience enhanced meteor activity despite the close approach of an active interstellar comet. This geometric separation demonstrates the vast scale of interplanetary space, where objects separated by only a few astronomical units can remain entirely isolated from each other's influence. Dust particles ejected from comets undergo gradual modification through space weathering processes that alter their optical and chemical properties over timescales of thousands to millions of years. Solar wind sputtering removes surface atoms, while micrometeorite bombardment creates amorphous surface layers that change the particles' reflectance spectra. These weathering processes gradually erase the chemical signatures that initially distinguished interstellar dust from solar system materials, homogenizing the composition of particles in the interplanetary medium over geological time. The gravitational influence of Jupiter acts as a focusing mechanism that concentrates dust particles from outer solar system sources into the inner planetary region, creating temporary enhancements in dust density that correlate with the giant planet's orbital position. Particles from 3I Atlas that pass near Jupiter during their outward migration may experience gravitational scattering that alters their trajectories significantly, possibly directing some particles back toward the inner solar system despite their initial outward motion from the comet nucleus. Laboratory analysis of interplanetary dust particles collected by high-altitude aircraft and space-based collection systems reveals the presence of materials that likely originated from interstellar sources, though identifying specific parent bodies remains challenging due to the mixing of dust from multiple sources. Isotopic signatures in some collected particles suggest formation in stellar environments different from our solar system, confirming that interstellar dust comprises a measurable fraction of the material present in interplanetary space. The thermal emission from dust particles heated by solar radiation creates infrared signatures detectable by space-based telescopes equipped with sensitive thermal sensors. The Spitzer Space Telescope and other infrared observatories have mapped the distribution of warm dust throughout the solar system, revealing complex structures associated with asteroid families, cometary debris streams, and the general background of interplanetary particles. The dust from 3I Atlas will contribute to this infrared background, though distinguishing its contribution from that of native solar system sources requires careful analysis of temporal variations correlated with the comet's position. Planetary ring systems throughout the outer solar system contain dust particles supplied partly by interstellar sources, including material from previous interstellar comet encounters that occurred before human observation capabilities existed. The ring systems of Jupiter, Saturn, Uranus, and Neptune serve as natural particle detectors that accumulate dust over millions of years, preserving samples of interstellar material within gravitationally bound structures where they can be studied through remote sensing techniques. Future spacecraft missions to these ring systems may provide opportunities to analyze interstellar dust particles directly. Computer simulations of dust particle evolution in the solar system environment predict that materials from 3I Atlas will remain detectable in the interplanetary medium for periods ranging from thousands of years for the largest particles to mere decades for the smallest grains. The gradual dispersal of this interstellar material throughout the solar system will create a permanent but extremely diffuse contamination of our local space environment with extrasolar materials, adding to the inventory of foreign substances that have accumulated over the solar system's entire history through encounters with previous interstellar visitors. The remnant magnetic fields embedded within Mars's ancient crustal rocks preserve memories of a planetary dynamo that ceased operation billions of years ago, leaving behind scattered patches of magnetized minerals that serve as fossil compasses frozen in stone. These magnetic anomalies, strongest in the heavily cratered southern highlands, create invisible magnetic umbrellas that deflect solar wind particles and charged cosmic rays with varying degrees of effectiveness. The patterns of magnetization follow no global organization, unlike Earth's dipolar magnetic field, instead forming a complex patchwork of magnetic domains that reflects the chaotic final stages of the planet's magnetic field generation. The intensity of these crustal magnetic fields varies dramatically across the Martian surface, reaching maximum values of several thousand nanotesla in regions where ancient volcanic activity concentrated magnetic minerals into coherent formations. By comparison, Earth's surface magnetic field averages approximately 50,000 nanotesla, making even the strongest Martian magnetic anomalies 10 times weaker than Earth's global field. Yet these feeble remnants represent the only magnetic shielding available to protect the planet's atmosphere from the erosive effects of solar wind bombardment that has operated continuously for billions of years. Orbital magnetometer surveys conducted by successive Mars missions have mapped the magnetic field variations with spatial resolution approaching 10 kilometers, revealing structures that correlate with surface geology in ways that illuminate the planet's thermal and tectonic history. The largest magnetic anomalies occur in association with impact craters formed during the late heavy bombardment, suggesting that the impacts occurred while Mars still possessed an active magnetic dynamo. The magnetic minerals within these impact structures cooled below their Curie temperature while aligned with the ambient planetary magnetic field, preserving a record of field orientations that existed 4 billion years ago. The absence of magnetic anomalies in the northern lowlands provides evidence that these regions formed after the planetary dynamo ceased operation, possibly through processes that involved extensive volcanic resurfacing or catastrophic impact events that destroyed any pre-existing magnetic signatures. The sharp boundary between the magnetic southern highlands and the non-magnetic northern plains corresponds closely to the global topographic dichotomy that divides Mars into two distinct geological provinces. This correlation suggests that the formation of the northern lowlands represents one of the most significant events in Martian geological history. Theoretical models of planetary magnetic field generation require the existence of a convecting liquid iron core driven by thermal or compositional buoyancy forces. Mars likely possessed such a core during its early history, when radioactive heating and residual heat from planetary accretion maintain temperatures sufficient to keep iron alloys in a molten state. The gradual cooling of the planet's interior eventually solidified the core, terminating the convective motions that generated the magnetic dynamo and leaving only the fossilized magnetic fields preserved in crustal rocks. The timing of magnetic field cessation appears to correlate with major changes in Martian atmospheric evolution, including the transition from a thicker, more Earth-like atmosphere to the thin envelope of gas that currently surrounds the planet. Without magnetic protection, the solar wind could interact directly with the upper atmosphere, stripping away atmospheric gases through sputtering and ion pickup processes that operate continuously whenever solar particles encounter planetary atmospheres. Computer simulations suggest that magnetic shielding could have preserved a substantial Martian atmosphere over geological timescales. Local magnetic anomalies create miniature magnetospheres around magnetized crustal regions, forming complex plasma environments where solar wind particles follow curved trajectories determined by magnetic field configurations. Spacecraft observations reveal that these mini-magnetospheres can trap charged particles in ways similar to Earth's radiation belts, though the low magnetic field strengths and irregular geometries prevent the formation of stable, long-term particle populations. The plasma physics operating in these environments provides natural laboratories for studying magnetospheric processes under conditions unavailable elsewhere in the solar system. The remnant magnetization of Martian rocks depends on the presence of iron-bearing minerals, particularly magnetite and hematite, that acquired their magnetic orientations during cooling from high temperatures in the presence of an ambient magnetic field. The stability of these magnetic signatures over billions of years requires that the host rocks remained undisturbed by significant heating, impact shock, or chemical alteration. The preservation of coherent magnetic patterns across large regions indicates that much of the southern highlands has experienced minimal geological modification since the planet's early history. Paleomagnetic analysis of Martian meteorites found on Earth provides additional constraints on the ancient magnetic field, strength, and orientation, though the limited number of samples and uncertainty about their original locations on Mars restrict the scope of such studies. Some meteorites show evidence of magnetic field exposure during their formation, while others appear to have been magnetized by shock processes during the impact events that launched them from the Martian surface toward Earth. The magnetic signatures in these samples complement orbital observations to provide a more complete picture of Martian magnetic history. The magnetic field measurements obtained during atmospheric entry of Mars landers reveal temporary magnetic disturbances caused by the interaction between spacecraft and the planet's magnetic environment. These observations provide information about magnetic field variations at altitudes between the orbital measurement height and the surface, filling gaps in spatial coverage that result from the limited orbital coverage of magnetometer surveys. The entry measurements also reveal how magnetic fields affect the plasma environment around rapidly moving objects in the Martian atmosphere. Seasonal variations in the strength and orientation of crustal magnetic fields result from temperature-dependent changes in the magnetic properties of surface minerals and thermal expansion effects that alter the geometry of magnetized rock formations. These variations remain small compared to measurement uncertainties for most surface conditions, but sensitive magnetometers can detect systematic changes that correlate with diurnal temperature cycles and seasonal thermal patterns. The temperature dependence of magnetic properties provides another tool for studying the mineralogy and thermal behavior of Martian crustal materials. The interaction between crustal magnetic fields and atmospheric dust storms creates electromagnetic effects that influence dust particle trajectories and charging processes during periods of enhanced atmospheric activity. Charged dust particles respond to magnetic forces in addition to gravitational and aerodynamic forces, potentially creating preferential dust transport pathways that correlate with magnetic field configurations. These electromagnetic dust dynamics may contribute to the complex patterns of dust deposition and erosion observed across the Martian surface. Comparative planetology studies reveal that Mars's magnetic history resembles that of the Moon, which also possesses localized crustal magnetic anomalies but lacks a global magnetic field. However, the Martian magnetic signatures appear stronger and more extensive than lunar magnetic anomalies, suggesting that Mars maintained an active dynamo for a longer period or generated stronger magnetic fields during its magnetically active phase. Venus, despite its similar size to Earth, shows no evidence of crustal magnetic fields, indicating that its high surface temperature has erased any magnetic signatures that might have been preserved in surface rocks. Future Mars missions equipped with sensitive magnetometers and drilling capabilities may provide direct access to subsurface magnetic materials that have been protected from space weathering and thermal cycling effects that could alter surface magnetic properties. Core samples obtained from magnetically anomalous regions could reveal the detailed magnetic history of specific rock formations and provide constraints on the intensity and orientation of ancient magnetic fields, with precision unobtainable through orbital measurements alone. The magnetic legacy preserved in Martian crustal rocks represents one of the most direct records available of conditions that existed during the planet's early history, when liquid water flowed across the surface and the atmosphere remained thick enough to support stable climate conditions. These magnetic fossils serve as silent witnesses to the dramatic transformation that converted Mars from a potentially habitable world to the frozen desert that has persisted for billions of years. Their orientations forever recording the direction of magnetic field lines that ceased to exist before complex life arose on Earth. The gravitational influences of Jupiter and Saturn reach across astronomical distances to exert subtle but measurable forces on the trajectory of 3I Atlas, creating perturbations that will alter the comet's path through space by amounts detectable only through months of precise astrometric observations. Jupiter, with a mass exceeding that of all other planets combined, dominates these gravitational interactions despite being separated from the comet by distances measured in astronomical units. The giant planet's gravitational field extends throughout the solar system, creating potential wells and gravitational gradients that affect the motion of every object within the Sun's sphere of influence. The mathematical description of these gravitational perturbations requires solving differential equations that account for the constantly changing distances and relative positions of all massive bodies in the solar system. As 3I Atlas follows its hyperbolic trajectory toward perihelion, the gravitational forces it experiences from Jupiter and Saturn vary continuously according to the inverse square law, creating accelerations that change both in magnitude and direction as the comet's position shifts relative to the giant planets. These variations accumulate over months to produce measurable changes in the comet's velocity vector and orbital parameters. Saturn's contribution to the gravitational perturbations remains smaller than Jupiter's due to its greater distance from the comet's trajectory and its smaller mass. Yet the ringed planet's influence still produces detectable effects on the comet's motion when integrated over the months-long duration of the encounter. The combined gravitational effects of both giant planets will increase the comet's departure velocity by approximately 2 kilometers per second, adding kinetic energy that Jupiter and Saturn derive from their own orbital motion around the Sun. This energy transfer represents an infinitesimal loss of orbital energy for the planets, but a significant velocity increase for the much smaller comet. The three-body gravitational dynamics governing the interaction between the Sun, giant planets, and the comet create what mathematicians call a restricted three-body problem, Where the motion of the least massive object, the comet depends on the gravitational fields created by the two more massive bodies. No analytical solution exists for this type of gravitational system, requiring numerical integration techniques to predict the comet's future trajectory. Modern ephemeris calculations employ sophisticated computational methods that can model gravitational interactions with precision sufficient to predict celestial positions decades into the future. Gravitational slingshot effects, first understood through spacecraft navigation studies, occur naturally when small bodies pass near massive planets on hyperbolic trajectories. The comet approaches Jupiter's gravitational sphere of influence from one direction and departs in a different direction, gaining kinetic energy in the process, while Jupiter loses an imperceptible amount of orbital energy. This gravitational assist operates according to conservation of energy and momentum principles, demonstrating how orbital mechanics can transfer energy between objects of vastly different masses through purely gravitational interactions. The timing of gravitational encounters depends critically on the relative positions of the planets and the comet during the approach phase, creating sensitive dependence on initial conditions that exemplifies chaotic dynamics in celestial mechanics. Small uncertainties in the comet's initial trajectory can lead to dramatically different outcomes for gravitational encounters, though the massive separation distances involved in this particular encounter minimize such chaotic effects. The comet will pass sufficiently far from both Jupiter and Saturn that the perturbations remain predictable and well-behaved. Tidal forces generated by the gradient in gravitational field strength across the comet's finite size remain negligible due to the large separation distances involved in the encounter. Unlike comets that pass very close to massive planets and experience tidal disruption, 3I Atlas will maintain its structural integrity throughout the gravitational encounter. The comet's nucleus, perhaps 2 kilometers in diameter, subtends such a small angular size when viewed from Jupiter that the gravitational field appears essentially uniform across the entire nuclear volume. The gravitational perturbations affect different components of the comet's motion in distinct ways, altering the orbital inclination, eccentricity, and orientation of the trajectory plane with respect to the ecliptic. The magnitude of these changes depends on the geometry of the encounter and the specific timing of closest approach to each giant planet. Orbital mechanics calculations show that the encounter will increase the comet's orbital inclination slightly while reducing its eccentricity by a small but measurable amount. Relativistic effects predicted by Einstein's general theory of relativity contribute additional perturbations to the comet's trajectory, though these effects remain orders of magnitude smaller than the classical gravitational influences of the giant planets. The Sun's gravitational field creates space-time curvature that affects the propagation of light and the motion of material objects, producing corrections to Newtonian orbital mechanics that become measurable only for objects with very precise trajectory determinations. These relativistic effects represent the limiting accuracy for predicting comet trajectories over extended time periods. The gravitational assist provided by the giant planets will determine the comet's departure velocity from the solar system, affecting how quickly it returns to the interstellar medium and which direction it travels through the galaxy after leaving the Sun's gravitational domain. Computer simulations show that 3I Atlas will depart the solar system faster than it arrived, carrying additional kinetic energy that will influence its motion through galactic space for millions of years. The trajectory modifications caused by solar system gravitational encounters may alter the comet's galactic orbit enough to prevent it from ever returning to this region of space. Observational verification of predicted gravitational perturbations provides rigorous tests of our understanding of solar system dynamics and the accuracy of planetary mass determinations. Any discrepancies between observed and calculated trajectory changes could indicate previously unknown sources of gravitational influence or reveal the need for refinements in theoretical models. The encounter thus serves as a natural experiment in gravitational dynamics, allowing astronomers to verify theoretical predictions through direct observation. The measurement precision required to detect gravitational perturbations pushes astrometric techniques to their fundamental limits, requiring observations accurate to milliarc seconds of angular position over time periods spanning months. Ground-based telescopes equipped with adaptive optics systems and space-based observatories both contribute to these measurements, with each observation adding incremental improvements to the determination of the comet's trajectory. The accumulated precision of hundreds of position measurements allows astronomers to detect gravitational effects smaller than the comet's own diameter, radio interferometry techniques that combine signals from telescopes separated by thousands of kilometers achieve the angular resolution necessary to measure minute changes in celestial positions caused by gravitational perturbations. These observations require careful correction for atmospheric effects, Earth's rotation and orbital motion, and instrumental systematic errors that could mask the small gravitational signatures being sought. The success of such measurements demonstrates the remarkable precision achievable through modern astronomical instrumentation. The long-term evolution of the comet's trajectory beyond the solar system will depend on subsequent gravitational encounters with nearby stars during its journey through galactic space. Computer simulations that follow the comet's motion for millions of years show that random stellar encounters will eventually dominate its trajectory evolution, overwhelming the small velocity changes imparted during its passage through our solar system. The gravitational modification provided by Jupiter and Saturn represents only a minor perturbation in the comet's cosmic journey. Future interstellar comets that enter the solar system will experience similar gravitational encounters with the giant planets, creating a natural selection process that preferentially accelerates objects on certain types of trajectories while leaving others relatively unaffected. This gravitational filtering effect means that the population of interstellar objects observed in the solar system may not represent an unbiased sample of the materials present in interstellar space, as gravitational encounters modify both the trajectories and the observational characteristics of visiting objects. The gravitational choreography performed by 3I Atlas and the giant planets represents a miniature version of the dynamical processes that have operated throughout the solar system's history, gradually modifying the orbits of countless small bodies through repeated gravitational encounters. These same processes shape the architecture of the planetary system itself, clearing debris from planetary zones and establishing the relatively stable configuration that has persisted for billions of years since the era of planetary formation concluded. Phobos and Deimos maintain their silent vigil around Mars with the mathematical precision of celestial clockwork. Two irregular chunks of captured asteroid material that complete their orbital dances in periods so brief that an observer on the Martian surface would witness multiple moonrises and moonsets within a single sol. Phobos, the larger and closer of the two moons, races around Mars in just 7 hours and 39 minutes, faster than the planet's own rotation period, creating the unique phenomenon of a moon that rises in the west and sets in the east. This retrograde apparent motion results from the moon's orbital velocity exceeding the rotational velocity of the planet beneath it, a circumstance found nowhere else in the solar system. The gravitational dynamics governing these tiny moons demonstrate orbital mechanics operating at the edge of stability, where tidal forces and orbital decay create conditions that will ultimately lead to dramatic changes in the Martian satellite system. Phobos orbits at an altitude of only 6,000 kilometers above the Martian surface, closer to its parent planet than any other known moon in the solar system. This proximity places the moon well within the Roche limit, the distance at which tidal forces from the planet exceed the gravitational self-attraction that holds the satellite together. Only the structural strength of solid rock prevents Phobos from disintegrating immediately under these tidal stresses. Deimos follows a more distant and stable orbit at an altitude of 20,000 kilometers, completing one revolution around Mars every 30 hours and 18 minutes. Unlike its companion, Deimos appears to move slowly across the Martian sky, remaining visible for days at a time before disappearing behind the planet during its orbital passage. The orbital period of Deimos nearly matches the length of a Martian day, creating complex synchronization patterns where the moon's position in the sky changes only slowly from one sol to the next. The irregular shapes of both moons reflect their probable origin as asteroids captured from the nearby asteroid belt through gravitational interactions that occurred during the early history of the solar system. Phobos measures approximately 27 kilometers in its longest dimension, while Deimos spans only 15 kilometers across its major axis. Both objects display the heavily cratered surfaces characteristic of bodies that have experienced billions of years of micrometeorite bombardment without the geological activity that might erase impact scars through volcanism or tectonic processes. Spectroscopic observations reveal surface compositions dominated by carbonaceous materials similar to those found in primitive asteroids, particularly those belonging to the D-type classification that populates the outer regions of the asteroid belt. The low reflectivity of both moons, they reflect only 6% of incident sunlight, results from the presence of organic compounds and hydrated minerals that give their surfaces the dark coloration typical of carbon-rich asteroids. These compositional similarities support the hypothesis that the Martian moons originated as asteroid belt objects rather than forming in place around Mars. Tidal forces exerted by Mars create measurable effects on the orbits of both moons, though the consequences differ dramatically due to their different orbital distances. Phobos experiences tidal acceleration that causes its orbit to decay at a rate of approximately 2 centimeters per year, bringing the moon gradually closer to the Martian surface. This orbital decay will eventually bring Phobos within the Roche limit, where tidal forces will overcome the moon's structural integrity and tear it apart to form a ring system around Mars. The timescale for this tidal disruption spans approximately 50 million years, a brief interval in astronomical terms that means Mars will likely possess a planetary ring system in the relatively near future. The debris from Phobos's destruction will spread around Mars in a thin disk similar to those surrounding the giant planets, though the ring particles will gradually spiral inward due to atmospheric drag and impact the planet's surface over periods of millions of years. This process represents one of the few examples of major changes in planetary system architecture that will occur within a time span short enough for humans to contemplate. Deimos follows the opposite evolutionary path, with tidal forces gradually expanding its orbit and increasing its distance from Mars over geological time. The moon's orbital period lengthens slowly as it spirals outward, eventually reaching distances where the gravitational influence of the Sun begins to compete with Mars's gravitational attraction. Computer simulations suggest that Deimos may eventually escape from Mars entirely, becoming an independent asteroid in solar orbit after millions of years of gradual orbital evolution. The libration of both moons, their tendency to keep the same face pointed toward Mars, results from tidal locking that occurred early in their orbital history, when tidal forces synchronized their rotational and orbital periods. This gravitational coupling ensures that the same hemisphere of each moon remains permanently visible from Mars, while the opposite hemisphere stays perpetually hidden from the planet's surface. The libration creates subtle oscillations in the apparent orientation of surface features as viewed from Mars, effects measurable only through precise photometric observations. Surface features on both moons include impact craters, linear grooves, and boulder fields that provide clues about their internal structure and geological history. The grooves on Phobos, first discovered in high-resolution images from orbiting spacecraft, may result from tidal stress fractures created by Mars's gravitational field or from impacts that shattered the Moon's interior. Some grooves appear to radiate from large impact craters, suggesting that major impacts can create fracture patterns that extend across significant fractions of the Moon's surface. The low escape velocities of both moons, approximately 11 meters per second for Phobos and 5 meters per second for Deimos, mean that objects launched from their surfaces with modest velocities can easily achieve orbit around the Moon or escape entirely into Mars orbit. A baseball thrown with reasonable force from the surface of either moon would achieve escape velocity, demonstrating the minimal gravitational attraction of these tiny bodies. This low-gravity environment creates unique conditions for future human exploration, where spacecraft landings and surface operations would require techniques developed specifically for asteroid encounters. Dust particles ejected from the Moon's surfaces by micrometeorite impacts follow complex trajectories determined by the weak gravitational fields of the moons and the stronger attraction of Mars. Some particles achieve escape velocity and enter independent orbits around Mars, while others fall back to the surface after following ballistic trajectories. The dust environments around both moons create potential hazards for spacecraft operations, as even microscopic particles can damage sensitive instruments when encountered at orbital velocities. Seasonal variations in solar heating create thermal stress cycles that may contribute to the gradual breakdown of surface materials on both moons. The extreme temperature variations from minus 140 degrees Celsius during eclipse periods to minus 40 degrees Celsius in direct sunlight cause repeated expansion and contraction of surface rocks that can lead to fracturing and the creation of regolith layers. These thermal cycles operate continuously throughout the Moon's orbital periods, gradually modifying surface topography over geological time. The gravitational influence of the Martian moons on the planet's rotation and tidal bulge remains negligible due to their small masses and the relatively large distances involved. Unlike Earth's moon, which creates significant tidal effects and gradually slows Earth's rotation, the Martian moons produce no measurable influence on their parent planet's rotational dynamics. This asymmetric relationship emphasizes the tiny scale of the Martian satellite system compared to the Earth-Moon system. Radio occultation experiments conducted when the moons pass behind Mars, as viewed from Earth, provide measurements of their gravitational fields and internal density distributions. These observations reveal that both moons possess relatively low densities consistent with porous, rubble pile structures rather than solid rock bodies. The internal porosity may reach 50% or more, indicating that the moons consist of loosely bound collections of fragments held together by weak gravitational attraction. Future robotic missions to the Martian moons face unique challenges related to their weak gravitational fields and complex orbital environments. Landing on either moon requires precision guidance systems capable of achieving soft touchdowns on irregular surfaces with minimal gravitational assistance. Sample return missions could take advantage of the low escape velocities to return substantial amounts of material to Earth using relatively modest propulsion systems, potentially providing direct samples of primitive asteroid material without the expense and complexity of asteroid belt missions. The Martian moons serve as natural space stations positioned at strategic locations for future human exploration of Mars, offering staging areas for surface operations and emergency refugees for crews operating in the Mars system. Their weak gravitational fields would permit construction of large structures using minimal structural support, while their positions in Mars orbit provide constant communication links with surface assets and Earth-based mission control centers. The inevitable departure of 3I Atlas from our solar system follows the same mathematical certainty that governs all hyperbolic trajectories, a geometric inevitability encoded in the comet's excess velocity that no gravitational embrace can overcome. As the comet swings around the Sun at its closest approach, reaching perhaps 1.5 astronomical units from our star, closer than Mars but still farther than Earth, it will achieve its maximum velocity relative to the solar system before beginning the long deceleration that will carry it back toward the interstellar void. The encounter with solar gravity serves as a cosmic slingshot that redirects the comet's motion without fundamentally altering its status as an unbound visitor destined for eternal exile in galactic space. The physics of the departure process mirrors the approach in reverse, with solar heating gradually declining as the comet recedes beyond the orbit of Mars and into the cold outer reaches of the planetary region. The coma that developed during the approach phase will persist for months as sublimation continues at decreasing rates, but the rate of mass loss will decline exponentially with distance as solar flux drops below the threshold needed to drive vigorous outgassing. Eventually, perhaps when the comet reaches the distance of Jupiter's orbit, sublimation will cease entirely, and 3I Atlas will return to the dormant state it maintained during its millions of years of interstellar travel. The gravitational assist provided by Jupiter and Saturn during the comet's passage will increase its departure velocity by approximately 2 kilometers per second above its arrival speed, ensuring that 3I Atlas leaves our solar system with more kinetic energy than it possessed when it first entered the Sun's gravitational domain. This additional velocity represents energy borrowed from the orbital motion of the giant planets themselves, though the mass difference between the comet and the planets means that Jupiter and Saturn experience no measurable change in their orbital characteristics. The energy transfer demonstrates conservation principles operating on astronomical scales. Radio tracking of the comet's position will continue for years after its closest approach to the Sun, providing increasingly precise measurements of its departure trajectory and final velocity vector. These observations will reveal the exact direction the comet travels as it returns to interstellar space. Information that constrains models of its future galactic orbit and the possibility of eventual encounters with nearby star systems. The departure direction depends on the precise timing and geometry of gravitational encounters with the giant planets, creating slight but measurable variations from the simple hyperbolic path the comet would follow if the solar system contained only the Sun. The transition from bound solar system visitor to free interstellar wanderer occurs gradually as the comet crosses successive boundaries that mark different spheres of gravitational influence. At a distance of approximately 1,000 astronomical units from the Sun, the comet will enter the heliopause region where solar wind pressure balances interstellar gas pressure, marking the effective boundary of the solar system's sphere of influence. Beyond this distance, galactic gravitational forces begin to dominate over solar attraction, though the precise location of this transition depends on the direction of travel and the local density of interstellar matter. Thermal models predict that the comet's surface temperature will drop below 50 Kelvin within a few years of departure, returning the nucleus to the frozen state that characterized its pre-encounter condition. The interior temperature will decline more slowly due to the low thermal conductivity of the ice-dust mixture, but within a century of leaving the inner solar system, the entire nucleus will return to temperatures near absolute zero. Any volatile gases that remain trapped within the crystalline ice structure will freeze solid, effectively ending all chemical activity until the comet encounters another stellar radiation source. The dust coma surrounding the nucleus will gradually disperse as solar radiation pressure and gravitational forces spread the particles across increasingly large volumes of space. The smallest particles will escape the comet's weak gravitational field entirely, joining the general population of interstellar dust grains that permeates galactic space. larger particles may remain gravitationally bound to the nucleus for extended periods, creating a tenuous debris cloud that will accompany 3I Atlas throughout its future interstellar journey. Spectroscopic observations during the departure phase will provide final opportunities to study the comet's composition before it fades beyond the detection limits of terrestrial telescopes. The decreasing production rates of gas and dust will reveal information about the depth distribution of volatile compounds within the nucleus. As different species cease outgassing at different distances from the Sun, these observations complement the data obtained during the approach phase to provide a complete picture of the comet's response to solar heating throughout its encounter with our stellar system. The orbital mechanics governing the departure trajectory create specific geometric constraints on the comet's future motion through galactic space. Mathematical analysis shows that 3I Atlas will travel at an angle of approximately 60 degrees relative to the galactic plane, following a path that will carry it through regions of the Milky Way containing varying densities of stars and interstellar matter. The comet's galactic orbit will bring it within a few light years of several nearby star systems over the next million years, though gravitational encounters with these stars will gradually alter its trajectory in unpredictable ways. Computer simulations that model the comet's motion for millions of years into the future show that random gravitational encounters with passing stars will eventually dominate its trajectory evolution, overwhelming the small velocity changes imparted during its passage through our solar system. The chaotic nature of stellar encounters means that predicting the comet's location more than a few million years in advance becomes impossible, as small uncertainties in initial conditions amplify exponentially through successive gravitational interactions with unpredictably positioned stars. The isotopic and chemical signatures acquired through interaction with solar radiation and solar wind particles will preserve a record of the comet's encounter with our stellar system long after it returns to interstellar space. Cosmic ray exposure during its interstellar journey will gradually modify these signatures, but some chemical changes may persist for millions of years as permanent markers of the comet's brief visit to the inner solar system. Future civilizations that encounter 3I Atlas millions of years hence might be able to detect these chemical fossils and reconstruct evidence of the comet's ancient passage through our region of space. The electromagnetic environment surrounding the departing comet will transition gradually from the solar wind-dominated conditions near the Sun to the interstellar medium beyond the heliopause. This transition affects the ionization state of gases in the coma and the electromagnetic interactions between charged particles and magnetic fields, creating measurable changes in radio emission properties that provide remote sensing capabilities for studying the boundary between solar and interstellar environments. The comet serves as an inadvertent probe of these transition regions. Long-term monitoring campaigns by ground-based and space-based telescopes will track the comet's fading brightness as it recedes from the Sun, providing calibration data for estimating the observational characteristics of future interstellar visitors. The rate of brightness decline follows predictable patterns based on the inverse square law governing solar illumination, but the specific details depend on the comet's size, composition, and rotation state. These observations establish baseline parameters for detecting and characterizing other interstellar objects that may visit the solar system in future decades. The departure of 3I Atlas marks the end of a brief cosmic encounter that provided direct samples of materials from another stellar system while demonstrating the universality of physical laws governing comet behavior throughout the galaxy. The knowledge gained from studying this interstellar visitor will inform our understanding of planetary system formation around other stars and the processes that operate in the cold interstellar medium between stellar systems. As the comet fades into invisibility, it carries with it trace amounts of solar system material that will eventually be dispersed through galactic space, creating an infinitesimal but permanent exchange of matter between our stellar neighborhood and the broader galactic environment. The mathematical certainty of the comet's departure reflects